Yeah, we are going to start in.
Yes, sure.
Now. Hello everyone. It's a great pleasure for me to introduce Pourya Forooghi. Pourya Forooghi is an associate professor at Aarhus University in Denmark. So I learned that Aarhus is the second biggest city of Denmark, the other side of the country with respect to Copenhagen. And there are direct flights from Paris to Aarhus, so we should go there more often. Unless of course you want to save on air travel. He completed his PhD at the University of Queensland, Australia in 2014 and subsequently worked as a researcher at the Institute of Mechanics-Karlsruhe Institute of Technology, KIT, until 2020 when he joined Aarhus University. Pourya is Villum Young Investigator in the period 2023-2028. Over the past few years, Pourya's research has focused on wall-bound turbulence, and his current research is centered on flow phenomena in water electrolysis for green hydrogen production. Pourya, you will start.
Yes, thank you very much. Is the voice okay? Okay, great. So thank you, Stefan, for the invitation and for having me here. So you already spoiled my first slide, that is about geography of Denmark. So, right, so yes, as you mentioned, Aarhus is, so if you look at the map of Denmark, a little bit of geography, you have this peninsula, and then we have a few islands, and Copenhagen happens to be in one of the islands, which is here. And then, but if you come to the peninsula, that's where you can find Aarhus, which is the second largest city in Denmark. And so the peninsula happens to be the more industrial side of the country, so you have some maybe familiar names around us. Probably Lego, of course, if you have a child like me. I'm not a fan of Lego myself, but I'm buying a lot of Lego. So. And then, right, so, and it's a nice place to visit. There is an almost direct flight. In summer, it's a nice place to visit. Because when there's a heat wave in Denmark, it's 25 degrees, right? So it's a nice place. But okay, in winter, it may be a bit darker. And right, so Aarhus University is, of course, by that extension, the second largest university in Denmark. We have about 40,000 students, about 10% of which are internationals, and these statistics may be a bit older. And we have 5 faculties, and the Faculty of Technical Sciences, where my department, which is the Department of Mechanical Engineering, exists. So it's kind of a straightforward structure. And right, so right now I'm leading or directing this small lab, which is called Heat and Fluid Flow Lab. And right now there are 4 PhD students and 2 postdocs in the lab, one of which have been visiting, been a visitor here, so some of you may know him, Michele, the first one. And so my research from many years ago centered on the wall-bound turbulence. So that's where I feel at home. And part of my research is also about wall-bound turbulence, especially on the rough walls. But of course, recently we started also looking into other problems, and that one of them is water electrolysis. And that's actually why we started this conversation or collaboration with Stefan and the people here. So, the main part of my talk will be about the first topic, because I have more to present, and then in the end I will talk a little bit about why we are looking into water electrolyzers and what is interesting and what is the future directions, because this is a very recent development. So, oops, I think I'm disconnected. I can see the presentation here, but maybe the cable is not yeah. Okay, now it's coming. I hope. I just clicked. I don't think it's enough movement. Okay, so well, of course, I need to motivate why roughness or rough surfaces are important. So there are many real-world applications in which the solid surfaces that are in contact with turbulent flows are not smooth, right? As a matter of fact, this is the rule rather than the exception, right? Smooth surfaces are rarely found. So some examples, if you look at inside a pipe or in a ship hull, or if you zoom on a turbine blade, or many other applications, you see that the surface is rough. And the main effect of roughness on the flow is, of course, a drag penalty. You have more drag on the rough surface. And it's important to remember that the roughness looks differently depending on where you look at. So in either of these applications, of course, the texture of roughness and the topography of roughness is different. And depending on that texture, the amount of drag penalty can be very different, even if you have the same roughness average height, so to say. So, and that's basically what motivates this research. Okay. I just use this. Success. No.
Move forward.
Yeah. Okay. Okay, okay, good. So I think I need your help every 2 minutes. This is going to take 2 hours, hopefully not. Okay, so sorry for showing this. I think everyone who passed Fluid Mechanics 1 knows this diagram, but it's mandatory to show it if you're talking about roughness. So this the so-called Nikoradze diagram in 1930s or 20s. These experiments have been done in Göttingen. So basically, they roughen the pipe with a uniform sand, and depending on the normalized size of this sand, if the Reynolds number is large enough, you have basically the friction coefficient only depends on the size of the roughness, right? And so that is what we call a fully rough regime. Now the question is, how about the case when you have a different type of roughness that is not the sand grain, which is of course the case most of the time. So if you have any arbitrary roughness, if you reach the fully rough regime, you match one of these sand grain sizes, and that's called the equivalent sand grain roughness of that surface. So basically, Ks, or equivalent sand grain size of roughness, is a sort of currency. Right? How rough is your surface? This is like this sand grain, right? So that's how we do. And the question is how we can determine this equivalent sand grain roughness size of the roughness a priori, because you can run the experiment and measure the drag and find it a posteriori. But it's expensive, and then there are many different types of roughnesses. And this quantity is what engineers would use, or if you run a RAND simulation, of course, that's the main input to a RAND simulation. So this is of engineering importance. Right, so just a little bit more of background. So let's say you have the sand grain of size Ks. So of course, if you have the inner sked velocity profile in a wall-bounded turbulence, you have this logarithmic region. And what happens when you have a roughness on the wall? You still have a logarithmic region because the roughness doesn't really affect the structure of turbulence in the log layer. But you have a downward shift, which is a manifestation of the added drag, right? So it's directly related to added drag due to roughness, and the downward shift is called, or delta U plus is what we call a roughness function, right? So the roughness function is added drag, if you want to if you want to simplify it. So for this sand grain, if I plot the roughness function as a function of the size of roughness in viscous units, if I reach the fully rough regime, you have a logarithmic function here, right? And if it's fully rough, if roughness drag is going to be independent of Reynolds number, of course, it's easy to show that the coefficient here should be 1 over von Karman constant. So this must be the case. Now, if I have any other arbitrary roughness and plot the resulting roughness function as a function of some physical size here. Let's say I take the peak to trough size of this roughness as k, and then do this plot. Of course, you have a logarithmic function with the same slope, but it doesn't necessarily fit into the Nikoradze asymptote, because the scale that I chosen may not be the equivalent sand grain size of that roughness. So, of course, you can scale it, and because it's a logarithmic function, eventually it will collapse into the Nikoradze diagram. And that scaled roughness size is your equivalent sand roughness. So that's how you can actually find this quantity by running experiments or so. So, well, the reason why this whole business started was in my institute. Someone, it's a very practical reason. Someone came to us and say, okay, I have this piston, like it's an internal combustion engine. There were a time when people did research on internal combustion engines. So it's quite old, I would say. Not very. Until 5-6 years ago, people still thought there is a future. And then they wanted to run RAND simulations on this surface, but they didn't know the equivalent sand grain roughness of their sample. And then the question is, okay, what is that? And there is no way to know it. And this is quite important if you want to run RAND simulations. So we basically scan this surface, and then we run numerical experiments, because it's much cheaper than the actual experiments, sorry. And they are not perfect numerical experiments, I have to say that. So basically, we run DNS of turbulent flow in this classical periodic box, right, with walls at the top and bottom. So basically, we put the rough surface at the wall of our domain, right? And then for the simulations, we use the Simpson, which is a pseudo-spectral solver developed by KTH people, like Philip Schlatter and his group. And then we also implemented an immersed boundary method, and the pseudo-spectral and immersed boundary are not the best friends, but somehow there was some suggestions that it can be done. And then we implemented that, and this is just an example of how the flow field would look like. This is the temperature contours on top of the roughness elements. I think temperature is a better way to visualize what you're doing. So, okay, now I think again some help because it doesn't go. Okay, now it works. So, well, we run DNS at different roughness heights, right? So when you change the Reynolds number, of course, the physical height of roughness in viscous units becomes larger and larger, and you see this downward shift, and you can measure it, and then fit into the Nikoradze asymptote, and you find the sand grain size of the roughness. So in this case, we determined that the sand grain size is 290 micron for this roughness, and this is the physical size that I put a scale here that you can see. And you cannot really find 290 micron anywhere in this picture. It's important to know that Ks, or the equivalent sand grain size, is not a physical size. It's like a flow quantity. It's not a measurable physical quantity. You cannot really find this anywhere. It has to be larger, otherwise you would. It's smooth, right? It behaves as smooth. I don't know. Well, actually, you can say this. K plus is here 10 to So basically, this K plus is what you're asking for, right? So it's about 70-ish. You can't go too high. That's a problem with DNS because it becomes very expensive. But you just have to go high enough to reach that asymptote, so which in our case is 70. And normally you need a RETA of 500 to 600 to get there. This is something one can discuss. So some people think that scale separation is not enough actually, but that's the best we can do. But this is good enough, I promise. Okay, anyway, so you cannot really find this scale. It's a flow scale, and that's the whole thing. So now anyway, we did this, but what we did was finding Ks a posteriori by running some experiments. Now the question is, there is a lot of motivation if you can somehow relate Ks to the geometry of roughness, which would be a priori, and then someone doesn't have to pay someone else to do a project and calculate it based on DNS, right? So, so basically, now here is the proposition. We want to find Ks as a function of x, and x is a set of geometrical roughness parameters. It's equivalent of saying I want to find the roughness function, then it's a function of x and Reynolds. So at this fixed Reynolds number, roughness function is a unique related to Ks. You can say the same thing about skin friction coefficient, right? And then the question is what parameters you should use. So if, let's say this is the roughness profile, it's of course always irregular, and yes. And then you can of course have the PDF of the roughness height. And there is the tendency to use, let's say, the moments or the properties of this PDF function of roughness height as the predictive parameters in such correlations. So you can use the RMS height, skewness, kurtosis, or just the max minus mean roughness height. And there is also some people use this so-called effective slope, which is the mean streamwise slope of roughness. This is not a moment of roughness height itself, but it's derivative. Let's first derivative in streamwise direction. And of course, there are such correlations existing in the literature, but so I have a couple of them in which effective slope or skewness or other properties are used, and each one of these correlations are derived by fitting some data, right? And then a few years ago, we just run a lot of DNSs for different roughnesses, and then try to figure out how good are these correlations compared to the DNS data. And this is the kind of error or scatter that you get. They are all around 1, right? The ratio of DNS and the model or correlation. But you have also quite a lot of scatter, and this is the state of the art, or this was the state of the art. And of course, there are many more correlations, but believe me, they are all more or less in the same range. So, and then what does it mean? Basically, what do we lose if you lose this predictive power? What does this error translate to? So there is this nice paper, Annual Review Fluid Mechanics from 2021, and I just take these estimates from that paper because it's kind of big claim. So they estimated that 10% uncertainty in prediction of drag. How much in dollars or euros it costs for different sectors, right? And the shipping sector, aviation sector, and wind farm sector will face a lot of uncertainty because they cannot, if you cannot predict the drag, right? So, and this is the type of figure that we use a lot when writing grant applications. So you see, it's an important problem, right? But I do it because I find it interesting. But of course, it's also important for real world thing. And if you have a heat transfer problem or mixing problem, the uncertainty can be even more significant. So because I mentioned heat transfer, I just have one slide on heat transfer. I think it's an important topic. So basically, we know that when you have rough surface, roughness increases not only the drag, but of course, convection heat transfer, right? So basically, you can calculate the Stanton number and CF, skin friction coefficient, and then 2 times Stanton number divided by CF is Reynolds analogy factor, which is a way to show how heat transfer and momentum transfer compare. So if you have boundary layer, a flat plate boundary layer with Prandtl number 1, of course. This factor is 1, right? It's, again, textbook stuff. So we calculate this factor for smooth and rough surfaces at the same Reynolds number and then plot it against Ks. And the interesting thing is what we learn from this plot is roughness, of course, increases both, but increases drag more than heat transfer. And which is not really surprising because you have, of course, pressure term in the momentum equation. And the big part of drag is because of the pressure drag on roughness, which doesn't have a counterpart for heat transfer. So it's expected that Reynolds analogy is broken for rough walls. And then we run quite a lot of DNS on different surfaces, and you can see this drop, and you can kind of correlate it. And we also found some old experiments at higher Reynolds number, and all the data more or less fit into the same trend. But I think the message was what I said. And also, if you look at the inner scale temperature profile, similar to velocity profile, you also have a thermal roughness function. You have a drop in temperature profile. And then if you plot it against Ks plus, if the y-axis here was velocity roughness function, by definition, all the data should have collapsed into the same line. But now that it's temperature roughness function, I have some scatter, about plus minus 25%. And you don't expect them to collapse. And this is the kind of uncertainty that you would get if you use Ks for thermal calculations, because they are not uniquely related. So I think I will continue with the drag problem. Right, so now the idea is, what if we use a higher order input to predict drag on a rough surface instead of just using a few parameters? What if we use a higher order input? And that input will be, so what if I use somehow the entire PDF of roughness height distribution as an input, and on top of that I also do include the power spectrum of the roughness scales, the horizontal scale, because actually we can have the same PDF and very different range of wavelengths, right? It doesn't affect each other. So that's the idea. And right, so in order to try this idea, we thought, okay, we need to have many samples with different PDF and spectra, right? And then try to fit a curve. And generating samples with different statistical properties by itself is not a trivial task, right? And so now we use some sort of mathematically generated roughness, and we call it a pseudo-random, and happily we found an algorithm already published. So you can basically prescribe the PDF and spectrum of roughness distribution, and then the output of this algorithm will be the actual roughness realization. And there is some randomness because it's a lower order input compared to the actual roughness that you get. So it's somehow still stochastic, but it's pseudo-stochastic because you still prescribe some input about what you want. And then, okay, here you see 3 different PDF functions and 2 different spectra, and the combination will give you 6 different roughness samples, and they look differently. For example, if you have a higher slope in your spectrum, it means that smaller wave numbers have larger, or large wavelengths have more contribution. And on the realization, you can see that actually you have kind of a larger structures in your roughness. So, but anyway, this is how we generate roughness. And then, of course, the question is, does this artificial roughness behave like the actual roughness? So we could get our hands on some real roughness samples, like scanned microstructures. So this is the combustion engine roughness that I showed you in the beginning. We also have some sand grain roughness, scanned sand grain, and some other samples. So on the left is the real roughness, and on the right is the one reproduced by this algorithm. You can see that they look more or less similar. I hope, yeah, you agree. But also when you run DNS for both real and artificial and then compare the roughness function, they are almost always on top of each other. So this is a true representation of the roughness. The other problem that you would face if you want to run a lot of DNSs is computational cost, because even one DNS is expensive, and as you ask and I explain, you need high Reynolds numbers. So this is extremely expensive. So one of the reasons, as some of you may know, why DNS for turbulent flows is so expensive is because you need a large enough computational domain so that you can capture most of the energy containing structures, right? And one idea is to use the so-called minimal channels, right? So you have channels that, so you basically reduce the size of your domain in span-wise and stream-wise direction. And this is a brilliant idea. Of course, it's unfortunately not my idea. We took it from someone else, but okay, we proved that it works actually. So, right, so if you make the domain smaller, what happens, I show here. So here on the right, you see the velocity profile. The dashed lines are the smooth wall, and the solid line is rough wall. So here, if you look at this, the blue profile, this is the full channel. So this is a healthy DNS in a full rough channel. And you see also the smooth pipe. So now if you reduce the size of the channel, at some point away from the walls, the structures are large and you are not capturing them properly. And then the profile starts doing some strange thing. It goes away from the normal healthy turbulence profile. But the interesting thing is both smooth and rough walls deviate the same amount, right? Because as I explained, and this is the outer layer similarity hypothesis, that roughness doesn't affect the structure of turbulence far away from the wall, except from its effect on the wall shear stress. That's the only thing that is affected. That's why both of them deviate the same amount. So if you subtract them, basically a minimal channel can give you the same roughness function, because what we really care about is the difference between the smooth and rough, not the absolute value. And this difference can be captured properly down to a certain size. So you cannot go smaller than a certain size, and that's why this gray curve starts to deviate already here. So you should be able to capture this so-called autonomous cycle of turbulence near wall, which is essential for turbulence. If your domain size is large enough, you can capture it. So with this idea, we could now do a lot of DNS, much more than anyone would be able to do it in a full channel, right? So, okay, the next thing is now we have an idea. We want to use PDF and power spectrum of roughness as an input and get the KS as an output. So our model is now a neural network, and the only reason we use it because we think it's a good way to fit a nonlinear curve, right? When you have a lot of input, right? As you have a high order input. So basically, as the input layer, you have the discretized form of the power spectrum and PDF. So we discretize it, and each one would be one input value or one input node. You have some hidden layers, and then the output would be the normalized equivalent sand grain roughness, right? And we normalize with the K99, which is, let's say, 99% interval of this PDF. Doesn't matter. K99 is just a physical scale of roughness, right? That we use to normalize. And I try to not to explain too much because this is not really important, but we try to use, so basically we randomize the roughness generation method, and we produce many roughness samples which are very different. And through some algorithm that we learned from other people, we picked the 80 roughness samples that are most informative that minimize the uncertainty of the model the most. So this is something that we call design of experiment or active learning or whatever. If you ask statisticians, they have a name. If you ask someone else, they have some other name. But that's what we do basically. We pick up the experimental points in a place that minimizes the uncertainty of the whole model. So here I show some of the samples some of the roughnesses that we use to fit this model to, and you can see we have quite some range. And here you see the range of PDF and power spectra. So we use Gaussian PDF, we have Weibull distribution, and we have bimodal. These are the type of PDF that people say can represent the roughness in real world based on what you learn from literature. So now the model could reach an accuracy of about 10% or less on the average error, and the max error is between 20 to 30%, and which, depending on who you ask, it can be just a marginal improvement or a great improvement. So, but I think this is a step forward. So basically, what we showed is that if you use a higher order input to these roughness models, actually you can reduce the error. And so why do we have 3 bars here? When you test the model, when we test the model, we split the test data into 3 data sets. The first data set is the test cases that are generated with the same algorithm. So we call it internal. These samples are not seen by the model, but it's generated with the same algorithm. So maybe there is still a little bit of familiarity because it's the same type that you trained with. And then the other 2 data sets that we use for testing, they are taken from the literature. So they are totally different in the way they are generated. One is from the literature, and one are these realistic scanned surfaces that we have, and you see we have a very low error across all 3 data sets. Okay, so I explain it in the next slide. I don't want to go too much into detail. So now the idea is we have some improvement, and we claim this is because we have a better input to the model. But the question is, maybe you have a better performance because you have better training data. How do you know? Is it because of the inputs that you choose for the model, or just because you have good data? So we trained 2 more models with the same input data, but with the same training data, but with different type of input that is more close to what, let's say, lower order input. And what we observe is that on the first data set, all 3 models perform very much the same. But on the data sets in which roughness is very different from the original, actually the model with high order input performs much better than the models that are basically simpler. So this is actually the generalizability that is actually improved when you have a higher order input. Okay. So I think, okay. So, okay, I need to go to the previous slide. So the original model is called PS. So we have PDF and spectrum or power spectrum. In the other 2 models, we use some parameters like skewness, kurtosis, or a combination of them, right? So now we don't have the PDF and power spectrum as input, but some reduced parameters, right? And then PA is short for parameter, and then I don't actually know what is PAM. This is something that my PhD student decided to name it. Anyway, these are the models that are trained not with PDF and PS, but with some selection of parameters in the. So the input is different, and the error increases, especially if you test it against a different type of roughness. But if you use PDF and PS, we claim that actually you have some sort of generalizability. They include enough information for the model to be able to generalize. Okay, so next thing, we thought, okay, we trained this neural network and there is a lot of physical data probably embedded in this network, which it's very hard to interpret because at least I don't know how to interpret how a neural network works. Maybe Paula, you can help us with that. But it's quite some headache, right? So we learned again from some machine learning people that there is this so-called layer-wise relevance propagation analysis. And what does it do? So when you have a model or neural network as a model, you have different layers. So the input, your input given is given at the first layer as a, let's say, as a vector, right? And then there is this way of calculating how relevant each input, each value of the input is to determine the final output of the model for a certain point, right? So let me give you an example. This is how I understand it. So let's say you are a neural network to classify these three photos. Is it a horse or cat or a bird, right? And basically, your model takes pixels as the input, right? To say, for example, this is a bird. Now, if you apply this layer-wise propagation or backward layer-wise propagation, whatever it is called, it gives some pixels a higher relevance score. So basically, it is telling that it is these pixels around the profile of the bird that are more important in telling if it's a bird or it's a cat. So if the pixel here doesn't really matter, right? So we thought, okay, what is our input? The input to our model is the spectrum of roughness, among others. So if we apply this technique to our model, we can somehow learn which wavelengths, which scales of roughness are relevant in determining the drag and which ones are maybe less relevant. And so here you see an example. So this is basically the spectrum for one roughness sample. This is the power spectrum. And the color shows the relevance of that wavelength or that wave number in finding the equivalent sand grain roughness. So you can see that this analysis is telling us, we believe it, that the smaller wave numbers or large wavelengths have less relevance in determining the sand grain roughness. And this is the smaller scales that actually give you the drag penalty, if you want. So one can or cannot believe this. So we tried to try or examine the idea. So now we have the spectrum of roughness. We filtered out so we use a high-pass filter. We filtered out the lower modes that, based on this analysis, we think are less important, right? So this is the original surface, and this is the filtered surface. So you can see there is a difference because the geometry has changed. Basically, use a Fourier filter and then just throw away some modes, and you get a new roughness. It's not very complicated. And then we run DNS for the filtered and original roughness. And what you observe is actually in the logarithmic region, they collapse. So even though you have very different roughness, the scales that we filtered out there were not really important in determining how rough this surface it is. Of course, you have some discrepancy near the wall because the geometry is different, but okay, this is a logarithmic plot, so this is very small portion of the flow field. Okay, and so we tried the same thing for a random selection of other surfaces, and in all cases, when we filter out the modes or the wavelengths that we think are irrelevant based on this analysis, then we have a collapse in the logarithmic region. So in all cases, the roughness function will be the same, even though you can say, okay, this surface and this surface look very different or somewhat different. And the lesson learned is that the larger wavelengths above a certain value don't really contribute to creating drag penalty. So if you have a hill that is not very steep, it doesn't do much, right? Okay, I think I will skip this, but okay, maybe not, actually. It's interesting. So, so there is this thing called sheltering that we found out. So basically, if you have a roughness, this is the topography of roughness. So the roughness peaks can be placed in the wake of the previous ones and then don't generate that much drag because you are in the wake. So you are basically sheltered by the upstream peak. And then, so we kind of used a very simplified analysis, so you can have some estimate of how the wake propagate behind a mountain or a peak. And then you can somehow estimate where are the peaks that stick out of this wake layer. And then this is with, we showed it with red profiles. And then you can also, because you have the DNS data, you can also try to see where the drag is generated. So where are the points where local drag is highest? And there is a very good correlation between where the drag is generated and where the peaks of roughness are not sheltered, right? And we think actually what we observed in the previous slide, right, that the large wavelengths don't contribute to drag. It must be related to the sheltering effect. So if you have a roughness feature whose slope is smaller than this wake propagation angle, it's pretty much unimportant, right, for determining the drag. So this is a cool idea, right? The problem is with the range of Reynolds numbers that we have, you cannot really change this angle too much and see if this hypothesis is valid or not, because you need to go to much higher Reynolds number to have a significant change in this angle. So this is for now a hypothesis, and I think I skip it. I mean the rest of discussion for now. So far, if I want to summarize, of course, you have high, we showed that if you have a higher order input in form of PDF and PS, you have more accuracy and more generalizability in predicting roughness function. The problem is this high order input is not available easily. So someone should go take a photo, and this is not easy. So in the end, I don't know how much we achieved, because in real world, people may just have a few pieces of information about roughness, but at least we know that now it's a compromise and where we can go. Also, we had this lesson learned about the scales of roughness. So now all I talked about was about homogeneous roughness. And this is, there is an elephant in the room, and the roughness in real world is not homogeneous, right? So, and that's something that I just need to make sure I'm not too much over time. Okay, I'm pretty bad. So please stop me when I'm speaking too much. So the question is, okay, the roughness in real world is really heterogeneous. That's what happens in real world. And so we started by looking at very simplified academic heterogeneous roughness. That is, you have roughness strips elongated in flow direction. So this is, I think, this is a hot topic for a few years actually in the turbulence community. And so, by the way, we thought, okay, for the smooth part of the wall, you also can have different elevations. And then what happens when you have this type of heterogeneous roughness, you actually observe the secondary flows normal to the flow direction. And the classical knowledge about roughness is roughness doesn't affect the core of the flow above, let's say, a few roughness heights. But this is a totally different picture. So you have structures arising from roughness that extend to the edge of the boundary layer. So this is a very unlocal problem, and it's known why we have this. This is basically secondary flows of second frontal type. So you have, so now the Reynolds stresses are not homogeneous in the span-wise direction, they have a gradient, and that creates some sort of secondary motion. This is similar to a square duct. So if you have turbulence flow in the square duct, you have secondary flows near the corner. This is exactly the same phenomenon. I mean, not exactly, but pretty almost the same phenomenon. And we also see that the sense of motion changes if you have the relative, you change the relative height of roughness and the smooth part. That was something that people observed in the community, and they kind of, so here we can show that this is basically the same thing, right? You can have both senses of motion in the same setup. I think what matters is these secondary motions, even though they are fascinating and there are a lot of JFMs written on this phenomenon, they really do not matter that much for drag. So they don't, okay, maybe some people agree or disagree with me, but they don't add drag or modified drag force that much. And there is a recent paper that they systematically showed that. So yes, so probably for engineering purposes, we should maybe focus on something that is much more realistic, and that is what we are doing at the moment. We are looking at the patchy roughness. So roughness in patches. I think it's a bit too much for today, and I'm almost at the end of my time. So I will just pass through these next few slides. If there is a question afterwards, we can of course discuss. But I think this is something that we are currently looking at, and of course for a lot of real-world applications, patchy roughness matters a lot. For example, on the ship hulls, you have these small creatures, these barnacles that stick to the ship, and they always come in colonies. So they kind of like to be in a community, so they don't spread uniformly on the ship. They have small colonies. So it's important to look at this type of roughness, and then we try to systematically figure out how you can find the drag penalty of patchy roughness based on the information that you already have for homogeneous roughness. So that's the main idea, and then I can basically explain later if there is an interest. Okay, so I think I moved past. Okay, before I move to the second part of my talk, of course, there are many people in the last few years working on this, on the results that I showed you. So maybe I started this, but the main work has been done by the PhD students and the students, and then so I have to acknowledge their contribution. They were the ones who did the work, and I'm just presenting, right? And of course, the collaborators from KIT, KTH, Melbourne, and AU, they also contributed a lot. So this is really a group work that I'm presenting. So the second or the last part of my presentation that I will try to keep it short is about what we are doing right now in my group, and which is the reason why we got in contact in the first place. And this is the fluid mechanics in water electrolyzer, which is very far from turbulence, right? But okay, there is a very strong motivation to look into these problems in the we are having this green transition, and these are very important technologies, but it's also a very fascinating problem from fluid mechanics point of view that that attracts me personally. So to be clear, and this is something that we started, let's say 1 or maybe 2 years ago now. So this is really, most of the things are still work in progress. So just to be clear, there are different types of electrolyzers, and I show you 3 main types here, and there are others that are maybe less mature. And what we are interested in is the first type, really, the alkaline electrolyzer. So alkaline is the oldest technology. It's been around since 30s or 40s. So there is less development activities right now on alkaline, let's say if you look at high-end research. But actually, I think from fluid mechanics point of view, and also from the applied point of view, alkalines are the most interesting, and we really are only interested in alkaline. And the thing is, alkaline is the only type of electrolyzer where you have bubbles, actual bubbles on both anode and cathode side. Alkaline is of high commercial interest. So by all projections, if green transition dream and the green hydrogen dream is going to be realized by 2030 or 2050, there are all these projections, alkaline is going to play a major role, or if not the major role, because that's what people are making right now. And I'm not saying that the other technologies are not promising, but this is just the realistic business projections. And these electrolyzers have very low or quite low efficiency of the order of 50 to 60%, right? While for PEM or solid oxide, the efficiency is much higher. So there is a lot of room. So it's an interesting fluid mechanics problem. There is a room to improvement, and if you improve a little bit, you can gain a lot, because that's what is going to make the future. And that's basically the motivation for us to look into this type of electrolyzers. For example, if you look at PEM, you need rare metals in PEM electrolyzers, and that's, I think, going to be a problem in the future. Yes. So if you look inside an electrolyzer, this looks something like this. So you have porous electrodes sandwiched between two channels. So you have the electrolyte coming in, and of course you need a diaphragm in between. It's most of the time just a porous diaphragm. It's not even a membrane. But okay, there are some suggestions to use membranes. And so basically, gas is produced on or inside these porous electrodes. Oops. So I borrowed this experiment, this visualization from my colleague. So they use neutron imaging to look inside this sandwich, and then at some point they turn on the electric current, and then you see that actually there is some gas produced near the membrane, right? So, and then, of course, porous electrodes are not the only type. So you can have, for example, perforated plates, or you can have a mesh. But I think porous electrodes are the most interesting, because obviously you have more surface area per unit volume if you have a porous electrode. And right, and so we have made some, or my colleagues made some analysis of the pore size. So here you have a nickel foam, which is a common choice for this porous electrode. And if you look at the cell size distribution, you have something between 400 and 500, or maybe 600. That's the dominant pore size. And of course, you can have different densities. You can have larger or smaller. But that's the range of parameters that we are working at. So basically, hydrogen and oxygen bubbles form on these ligaments, right? And then grow. And then we also know for a long time that the size of these bubbles are of the order of the largest, maybe 100 micron. At least that's what we learned from older electrolyzers. So the bubble size is much or fairly smaller than the pore size. So the bubble actually can move, ideally can move freely after detachment and rise through this porous electrode or go up. And of course, I think in this group it's general knowledge that if these bubbles are bad for the efficiency, because they cover the surface and they also reduce the conductivity, the ion conductivity. So we run some very simple, basic simulations, not simple, but basic simulations, some low fidelity simulations, because this is a multi-physics problem. A lot of phenomena just contribute. You have electrochemistry, you have mass transfer, you have bubbles, a lot of things. And it's impossible, very difficult to run a DNS, including all the phenomena. So we just use some low fidelity multi-physics simulations just to get a feeling of which phenomena or the actual cell performance is sensitive to which one of these phenomena, right? So this is basically what you see here is a so-called polarization curve. I think most people must know it. So on the y-axis is the current, or on the x-axis is the current density, which is roughly the amount of hydrogen you produce per unit size. And on the y-axis is the cell potential, which is roughly speaking a measure of the efficiency of the cell, right? And so right now what I show here is two sub-phenomena that we looked at. And this is, again, a low-fidelity model. There are a lot of closure models going into it that are not probably very accurate. So really the goal here is just to get a feeling of what phenomena can be more important for the overall cell performance. So when this curve goes up, it's bad, and when this curve goes down, it's good, basically. It means that you have better efficiency at higher current densities. And then we look first at the coverage. So there are some models that tells you how much coverage you get. And then you see that actually you have some sensitivity to the amount of coverage of bubbles on the electrode surfaces, especially at higher current densities. We also varied the Sherwood number. So we looked at the mass transfer between the electrolyte and bubbles. And again, this is modeled with a simplified just prescribing a Sherwood number. We don't resolve the interface of it. And interestingly, the cell performance wasn't that sensitive to the Sherwood number. And I mean, if you think about it, when you have a lower Sherwood number, you have a higher supersaturation. But eventually, at least what we learned is eventually bubbles will form. Even if you have a higher supersaturation, at some point the bubble will form. And still, there is much more hydrogen in the bubbles compared to what is dissolved in the liquid. So at least in this range, and we chose this range of Sherwood number between 1 and 10, and that is the realistic range. Maybe if you go much higher or much lower, you see an influence. But I don't think in real world you have very different, range of Sherwood numbers. So this was just a first attempt. And then maybe I show later the videos, because there are some videos that I cannot show public. I'm not allowed to. But we observe that actually what happens in reality is that when you have a real like a porous electrode, these pores you can have gas pockets forming inside the electrode. So we use X-ray to look inside the electrode. There are gas pockets forming inside the electrode that are much larger than pore size. So somehow, let's say tens of pores are suddenly filled with a lot of gas, and essentially they are not going to produce any hydrogen. And so that's really what happens, the really chaotic world inside porous electrode, right? But then before we know that, we just try to break down this problem into simpler problems and look into that one by one, and eventually reach the most sophisticated problem. So one of the problems that we just started looking at, of course, we use a basilisk and we run direct numerical simulations. So it's a raising bubble through a pore network, and this pore network is very simplified. Basically, you have parallel cylinders as your pore network. And we also assume that the cylinders or this porous or these filaments are perfectly wetted. So there is no contact line issue, which would be, I guess, a bit difficult, at least at the first stage, to take into account. And then we also changed we covered some parameter space. We varied the Bond and Galilei number a little bit to see how it affects the flow. And we also changed the pore to bubble size diameter. And what here is the bubble path at different parameter combinations, right? So here you have a very low Bond number. This is basically a hydrogen bubble of 1 millimeter diameter, right? We couldn't, if you go lower, the time step will become too small, and then we have to find a way to actually do it. But we could go down to Bond number 0.1 without much problem. And then when the bubble becomes more and more deformable, so we keep the Galilei number the same, increase bond number, you see a less, let's say, chaotic looking path. And an interesting phenomenon that we observe is when the bubble is pretty stiff and the pore size is small, you have a high, so the problem is becomes a bit chaotic in the sense that it's very sensitive to the initial conditions. So if you change the initial location of the bubble a little bit, you have a different path, which is not too much unexpected, but this is quite interesting at least to observe. And at some point when you have a larger pore and a less deformable bubble, higher bond number, this sensitivity to the initial condition disappears, right? So, but this is, like, as I said, very recent results and work in progress. Another problem that we look at, and of course we reached out to Stefan for consultation, is the problem of coalescence. So when two bubbles, and then of course Wei can tell us more about this later. When you have two bubbles coalescing on a surface, of course, because of this surface energy that is released, you have a jump off, right? And the question is, what coalescences can lead to jump off of the two bubbles and which cannot? Because it's really the size at which the bubble leaves the surface is very important, especially in the light of what we learned about the electrodes being filled by gas. So, and then I cite this, I readapted this figure from a recent article by Demir et al. This is basically Twente group and Krug's group at Aachen, right? And they generated this very nice map experimentally. So I just try to translate it to you. So on the X, so we have jumping and sticking regimes after the coalescence of these two bubbles. And then on the x-axis, roughly speaking, you have the contact angle. And on the y-axis, you have the Ohn-Sorge number. So if you go up on the y-axis, you have high, basically high dissipation, right? Viscous dissipation. And so if you're on this branch of the plot, the dominant phenomenon that determines if it sticks or jumps after coalescence, it's basically the adhesion form. And if you are in this regime, basically the dominant phenomenon is dissipation, right? So even if you have zero contact angle, which is here, and we run some DNS, so Michele, the PhD student who was here, he runs some simulations with zero contact angle, right? Which is basically here, right? And then you can see at some point, even though there is no adhesion, there is no contact angle, at some point the dissipation is so strong that it dissipates all the released energy and you don't have a jump off, which is the blue shades if you look at this plot, and the red shades are the jumping ones here. And an interesting thing that we learned was that in order to initialize this simulation, you should initialize the contact. So if you let the bubbles meet each other, growing and meet at some point, we got a lot of artifacts, but maybe we didn't find the right way to do this. So we just initialized by saying that the two bubbles are already one bubble, right? And then let it evolve, right? And then currently we are looking at this regime. So now we have the contact angle, right? And these are very new data. I'm not even sure if they are correct or not. So, but I'm showing because I want to tell you what we are doing right now. So basically you have two bubbles coalescing on a flat surface with different contact angles. And so at some point you go from jump to no jump. If the two bubbles are on a cylinder, you can have a different picture. And also the orientation of the two bubbles, how are they located on this cylinder? That also can determine the jump. Right, but again, this is very, I just got this data yesterday, so I don't even know if they are correct. But and the motivation for looking at the cylinder is because if you look at these porous electrodes, the filaments are more or less like cylinders. They are not actually cylinders, but that's much closer than a flat surface to what we see in the real world. So, of course, the next step or next steps for us would be to get closer to the real world problem. So if you look inside this porous electrode, very roughly speaking, a porous cell looks like this, very simplified form. It's like a, I don't know how you call this shape actually. It's a decatetrahedron, something like that. So this is how it looks like. So we really hope at some point we can have growth of bubbles on these filaments and somehow approach this problem. And also we look at bubble rise through a realistic metal form. It's a long way to go. Maybe we don't get to the end of this thing, but at least we have started it. And in the end, we want to have a better picture of under what conditions the gas is entrapped inside these pores, because it seems to be an important thing. Right, and in the end, I should thank everyone, all the foundations who funded this research, especially because this video is going online. I have to thank them, but of course, without their help, it wouldn't be possible. And also thank you for your time, and I think I'm pretty much over time. Sorry for that, but if there are any questions, I'm happy to take. Yes.
Very much. This was fascinating. Sure, there are lots of questions. Yes, Paula.
Thank you very nice talk. Question mostly on the first part.
Yes.
Paula, take the microphone because people online maybe cannot hear your questions.
Yeah, I was saying that I have questions mostly on the first part.
Yes.
And well, you have looked at this, let's say, sand grain-like roughness.
Yes.
And so you model it with sort of random Gaussian processes, etc. And then you are trying to move this to this inhomogeneous roughness. But in many cases, you have structural roughness. For instance, deriving from additive manufacturing procedure where you have stripes. That's not like spots of like roughness, but it's more like
directional preference.
Exactly. So, are you planning to look into that?
I mean, we also looked at that. I mean, I skipped that part because for me, heterogeneous is more, for some reason, sounds more interesting for me. But we also looked at that. So, so we published something last year actually on the anisotropic rough. So like turbulence, roughness can also be heterogeneous and anisotropic. So basically we looked at anisotropic roughness. Maybe I can share it with you later. So basically you can also generate an anisotropic roughness because you can have the 2D wavelength spectrum, right? And then you can give it a directional distribution, right? So we could generate it, and it's there is very little done in that direction. So, but I think
in that case you may need more parameters to describe
exactly.
You have this effective slope.
Exactly. So there are some parameters suggested in the literature, like the ratio of the effective slopes in the two directions, right? Or the ratio of the correlation length of roughness in the two directions. And it's claimed that you can just use that and add it to the previous parameters, and then this is enough. We looked into it, and then the results is not quite the actual thing. Problem is a bit more complicated, but also we should remember that at least for the engineering sense, you can't have too complex models. So still probably we need to end up with a compromise, add a few parameters to what we already have, and then try to work on to use it for heterogeneous or non-isotropic. But the complexity is also the direction of flow with respect to the direction of anisotropy, like the main axis of this this whatever you have. That can also be a parameter that is, so there is a lot. I mean, people spend years on this homogeneous roughness and they are still doing things. And I think at some point the community should really look into the more realistic and maybe more difficult questions to answer. But yes, I can share with you later.
The DNS resolution, because I was wondering, in the DNS, if you have very small roughness elements, well, in your DNS you are resolving the Kolmogorov scale, right?
Yes.
But what if the roughness elements are below the Kolmogorov scale? Probably you don't care about resolving them.
They don't matter.
They don't matter.
Yeah, we don't.
So you basically have this spectrum, but you truncate the spectrum so
exactly.
that.
That's why.
I know. That's so they don't matter. Depends. I mean, how small they are compared to the Kolmogorov scale.
Yeah, exactly. So I mean, because we have wall bounded, it's mainly wall units. Because Kolmogorov is maybe more relevant a bit far away, but it's the same thing, right? But so if we believe Nikoradze, if you have roughness P feature that is smaller than about 5 in viscous units, it should be unimportant. If you believe
because
that.
Because it was a little bit related to when you show that if you filter the roughness, basically the results don't change.
But
much.
this is, we filter the high.
I know.
The higher level. But the lower ones are already filtered because of the numerical. We don't discretize them. And again, the argument is that they are too small to matter. So even if you solve them, and there is actually systematic work by Angela Busse, probably. They really try to answer this question. I mean, maybe 10 years ago, they have this paper that they filtered more and more of the small scales, and they say, okay, at some point they don't matter if you resolve them. But valid question, but for practical reasons, we cannot capture them, and then I have to justify it, and that's the justification.
So you pre-filter your roughness.
Yes, it's pre-filtered, exactly. Yes.
I have to teach, so
Yes. But thank you for your questions.
Thank you for the presentation. It's a little bit related. I didn't understand very well when you talk about DNS with a rough surface.
Yes.
What does this mean? So how you discretize your system in the wall that is rough?
So basically, it's an immersed boundary method. So you just don't. The mesh doesn't have to, immersed boundary method. The mesh doesn't have to follow the surface, right? So you have this mesh that is it's a spectral code, so we cannot even change the mesh. It's basically Fourier and Chebyshev, so it has to follow some distribution that is predetermined, and maybe it's not the most efficient distribution, but we just don't touch it, right? We inherited this pseudo spectral code that was working fascinating, and we had little time, so we look, okay, how we can implement an immersed boundary method. And then so the domain wall is the actual wall, is a boundary of the domain. Let's say you have spectral solver, right? So in the y direction you cannot have Fourier mode, so you have Chebyshev mode that gives you the possibility to have no slip on the wall, on the bottom wall. And then roughness is of course through immersed boundary method. So basically you have a force, you add a force to your continuous domain, and that force is smoothened around the boundary. And then, of course, because it's a spectral code, it gives you some Gibbs phenomenon, and then there are ways to handle that. I mean, based on the reference that we use. So if that's a question, basically the roughness is modeled through immersed boundary method, it's not moving.
How many grids you have for the?
Exactly.
If you have the maximum height of the roughness, how many grids you have?
So you can't have any roughness. So you can have, as Paola mentioned, you can't have very small roughness features, because then your mesh should be much finer. But on average, we put 100 points
100?
in one, let's say, bump, in one feature. So you should, and this is very crazy high resolution.
Yes.
Actually, I have to admit that we are kind of brute forcing, or we were brute forcing these simulations because, yeah, we had to. And also it's important you have very fine resolution, because then you have this Gibbs phenomenon that is added to the spectrum of your turbulence, but you want these scales to be separate from the scales of turbulence, right? So there are a lot of reasons why you shouldn't use immerse boundary method together with spectral code. But we were looking for a practical solution, and that works perfect, because pseudospectral code is very fast. So even though we overkilled the numerics, but still it was doable for us.
Very quick.
Yes, of course.
And so once you have fit your model,
Yes.
can you replace this roughness by a flat surface and something?
Okay. Yes. But then it's not a DNS anymore. It's a model, right? But there are.
But
models.
people do this.
People do it. So you can add a body force instead of the roughness, right? So you have a body force that somehow mimics the roughness that you remove, right? So you can add a body force that now gives you. So we also have a paper on that, how to actually, because this body force can be anything, right? Yeah, it can be done,
Okay,
but
okay.
it's then a model. It's not
Okay,
DNS
okay, yes.
anymore.
Okay.
Yes.
Yeah, thank you very much. You mentioned that there are many models, theoretical models, let's say, for the equivalent friction on rough surfaces.
Yeah.
So a family of models I'm thinking of are the models which are used for atmospheric boundary layers, so flow over topography. So, for example, there are the papers in the 90s by Hunt, Belcher and Hunt, for example, and also the homogenization techniques by Temam, multi-scale approach. Is that something you looked at, or?
I think that follows the previous question. So it's a homogenization model. I'm not familiar with specifically models in the atmospheric boundary layer community, but of course there are these homogenization techniques. But what I talk about, this equivalent sand grains size, it's even one step further. So you don't want to. The model gives you one quantity that an engineer can use to estimate the drag. So what you're saying is you homogenize the roughness, and then there is also this, there are some papers in the context of LES, for example. You have some roughness features, right, that are large enough to be resolved, and then the smaller ones, so you have a subgrid roughness model. So they exist, right?
But it could be connected to your learning approach, right? The fitting you do can be based on fitting an actual. For example, the Belcher and Hunt models, they are essentially asymptotic expansion around the potential for solution and so forth.
Yes.
And so they actually tell you how for example, they depend on the higher order modes of the roughness, but with unknown coefficients. So you, of course, you could learn these coefficients.
That was what I wanted to do actually, but the funding was over. Exactly.
So there would be
there's a lot
between learning everything, right? Not assuming anything about the modes you are going to learn, right? And you put all the spectrum and you think, and something which is more informed by an upstream theory.
I mean, one limitation that we have is because we use minimal channels, we cannot have very large wavelengths, or if you want them, then it becomes very so. Of course, I don't show you the bad things, but there are quite some limitations on. Yes, so if you go to the atmospheric context, I don't know if we can capture all the things that matter. But the fact that high wavelengths don't contribute that much, and actually you can resolve them if you want, this is some relief that, okay, with these minimal channels, we can still learn most of the things that matter. But good, so maybe I should write a proposal on that. But valid question. Thank you.
Maybe we will.
So thanks for the talk. I have just two questions, which are kind of intertwined. Like one is like, what is your quantity of interest when you try to predict drag for heterogeneous, sorry, for like, staggered roughness.
Yes, yes.
That, and then like, if you think that like for those kind of roughnesses, even that they are like experience different like mean flow profiles due to like change in the arrangement of the roughness, or like change even in the Reynolds number and so on, like if it would make sense to, instead of inferring like a single quantity of interest, maybe inferring like the whole velocity profile distribution as a function of the height instead.
That's a very good question. I mean, also it again goes back to the previous two questions. So you can just learn one quantity, or you can learn more things, like exactly some flow like a way to kind of find the local flow profile instead of finding one quantity. So right now we are still focused on the most simplified, or most I don't know how to describe it, basically drag coefficient of the entire surface. Because again, if you are a ship manufacturer, you want to know what is the drag on your ship, so you don't. But of course, as researchers, we are interested in more. And right, so right now it's really the drag coefficient that we try to look at. But I mean, an interesting way to put that, your question is, at what point, actually, if you have a heterogeneous roughness, flow reaches an equilibrium? Because if you have a large enough rough patch and large enough smooth area, at some point turbulence reaches equilibrium, and you don't care about okay, you care a little bit about history, but at some point it's large enough. And there is actually literature on that, mostly for very simplified streamwise. So this is your boundary layer, here is smooth, and here is rough, right? And then how long it takes for the flow to reach equilibrium. And that depends on what properties of turbulence you are looking. So if you are only interested in mean profile, it's estimated, and of course I also had the results here. 10 boundary layer thickness is enough to reach the equilibrium if you are interested in mean velocity. If you are interested in second order statistics, I don't have the results, but there are groups who work on that, and it takes more. Right? And if you are looking at high order statistics, never. I mean, as long as people can do experiments, they never reach the equilibrium. So it's a more fundamental question. This is a also very interesting question. And the problem happens near the border where you have all the non-equilibrium effects. So I didn't answer your question. I just gave more questions. But this is, I think, the nature of this problem. Yes.
Maybe we will thank Pourya after this wonderful talk.